Well, a warm welcome to everybody. Thank you for joining. This is going to be a bit of a longer one, that's for sure. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you, pretty much out of nowhere. And today we have a hefty set of problems, 3 problems, simulating the free response with graphing calculating abilities permitted. So we have access. In this case, we're going to be using Desmos. You might be able to see that I'm also sharing my Desmos tab. So we'll be able to take a look at some of this. Although, as usual, I encourage you to do as much as possible without a calculator. And only when absolutely necessary should we use the calculator. That being said, the caveat to that is the AP exam is timed. So the faster you can do it, sort of the better. However, I really want to emphasize getting you guys into good habits when you're taking your test and writing down conceptually what you need to do, because that's where most of the points are awarded. So even though calculators are allowed for the whole problem, some of the basic stuff you won't really get points for just by using a calculator. So understanding what you're doing is a lot more important. I'm going to scroll through the first 3 problems, well, the 3 problems that are going to be featured in this video. You can take a look at them, write them down. You might also want to get yourself ready with like a glass of water or something if you want something to drink near you while you're working. That's fine. You could always pause the video, of course, but it's going to be a bit of a longer one. That's what I'm saying. Here's the second question. Feel free to pause the video, write this stuff down. These problems are courtesy of University of Houston, once again, coming through with some juicy AP problems. These are from the AB section, so of course it's open to any AB or BC student. Both should know how to do this. Give yourself 40 to 45 minutes to complete these problems. Try to do it all in one run because that really simulates what's going to happen on the exam. You're not going to get 15 minutes on one question and then they just kind of pause and you get 15 minutes. No. In fact, you're going to have access to all of the graphing calculator questions at once, and then independently you'll have access to all the non-graphing calculator problems at once, and you just get a big fat chunk of time. How you choose to use that time is up to you, but the average amount of time per question is 15 minutes per question. Okay, I think that clears up everything that we need to before we finally jump in and get started. So if you've given yourself a chance to do this, if not, pause the video, take a moment, try to work this stuff out for yourself. And then when you're ready, come back, join us, and see how we do it here. All right, let's get started with problem number 1. I see this line and I see 2 regions. Here's R, it's underneath this curve, this blue curve. And then I see S, which is in between the line and this blue curve. So if I want to find that area, you'll notice that if I do it dx, top minus bottom, the boundaries change right here. The boundary goes from the x-axis to this blue curve. So if I could calculate my area from right to left, from 0 to whatever this point is, that is one way that I could possibly approach this. These are the kinds of things that I think about if I were starting an AP question. F of x, this is obviously the blue function, so I'm going to highlight that. And the line, okay, 18 minus 3x. The line is tangent to the graph, so that means that it touches, it has the same x and y value, but it also has the exact same slope. And it's really easy to figure out this slope. We know that that one has a slope of negative 3. Therefore, at this point, we know that this function also has a slope of negative 3, just at that point. So that's helpful. Let's see, the region S, bounded by the graph of this polynomial and the line, and then region R. Oh, I think they misprinted that. Oh no, they didn't. They just didn't mention R yet. They'll probably mention R later. Yeah. I'm surprised they didn't mention R though. Anyways, show that the line is tangent to the graph at the point x equals -3. Okay, so they've given us a nice clue of what to do. We need to show that it's tangent. I mean, they did say that it's tangent, so that kind of helps. Because the slopes need to be the same, which means that f prime of -3 must equal -3. That's the slope of this line. And of course, f prime of x, which is the derivative of f of x, that's just going to be 8x minus 3x squared. And so therefore f prime of -3 is going to be -24 minus 3 times 9. Oh wait, is it a plus? No, it's not a plus. Oh, x equals 3. Silly me. What am I doing? So yeah, this is a plus 24 minus 27, which of course is -3. So that proves that the line is tangent, or does it? Well, it's great that they have the same slope, but this also has the same slope, and yet it's not tangent. This also has the same slope, and yet it's not tangent. So what's the idea here? We need to prove that the points are the same. So we need to say that y of 3, which is the line, is also equal to f of 3, which is the polynomial. So let's just make sure that's true. 4 times 9 minus x cubed, so minus 27. We need to make sure that that equals -3 times 3 plus 18. And I guess I wrote it in a slightly different order, but same thing. 18 minus 3 times 3. Yeah, and that leads us to say that 9 equals 9. Well, guess what? It do. 9 do equal 9. So we know that the points are also the same location. All right, so we've proven now that it's tangent. So tangent always means that it touches, means the point is equal, and the slope. Okay, now part B, it has us find that area of S. Interesting. Now the problem with what I mentioned earlier of trying to do this dy is that I can't easily turn this into I can't take the inverse of that very easily, 4x squared minus x cubed. So I don't think I'm going to want to get a function x equals g of y, which equals f inverse of x. Yeah. So we probably don't want to develop an inverse to integrate that. So what we're going to have to do is we're going to have to integrate dx, but that means that we will split this region like that, because we need to include this portion which has its own 2 separate boundaries, and this portion which has its own 2 separate boundaries. Got it? So the area of S, let's just represent it first. And notice we haven't used a calculator for anything. We're just going to represent the area of S. This is going to be the integral from that point 3, x equals 3, that's this spot here, from that point all the way to wherever this is. So we need to find out where that is. We can find out where that is by saying 4x squared minus x cubed equals 0. And if we factor out x squared, then it becomes clear that that 0 is located when x equals 4. Okay, so we're going to go from 3 to 4, top function, 18 minus 3x, minus bottom function, 4x squared minus x cubed, dx. That's part of the area. That's the portion of the area that goes from here to here, with the function f of x as the bottom and the line 18 minus 3x as the top. But then we need to add this portion which is only contained by the line. And of course, when does this line cross? Well, this line crosses when y equals 0, which means 18 minus 3x equals 0, which means x equals 6. So we're going to add the integral from 4 to 6 of this line. And really, you could just like calculate the area of that triangle if you wanted to just do that process very, very easily, because now this is just like a perfect triangle with a base of 2 and a height of 6. So base of 2, height of 6. It's not drawn to scale, clearly. But yeah, it's just going to be 6. And then this, if you really want to use a calculator, I mean, by all means, go ahead. It saves you time. I understand. So I'm not going to get upset or disappointed or whatever that you're using a calculator, because those are the tools that you are granted. So let's take a look at what this is. We have integral from 3 to 4 of 18 minus 3x minus 4x squared plus x cubed. And we have to put this in parentheses because it needs to understand that all of this is the integrand. And there we go, 19.166. So it seems like 1.9 and 1/60th. 1.916 repeated, and then we're going to add 6, of course, so this leaves us with 7.916 repeated. That is the area under the curve, or the area of S, which is under several curves. Okay, let's look at part C. Part C says find the volume of a solid generated when R, so that's this underneath the blue curve only, is rotated about the x-axis. So as far as that portion of the graph goes, something like that. Let's make it 3-dimensional. Remember that this is located at 4. We solved that earlier, and we're going to be rotating this so that we have these like 3-dimensional slices, basically. Okay, so each cross-sectional slice with the x-axis at the center has a radius equal to the function f of x. So this radius is simply equal to 4x squared minus x cubed. Therefore, the area of each of these slices is pi times 4x squared minus x cubed quantity squared. And now we can just throw this into an integral. Right, we're just going to integrate from 0 to 4. This stuff could be done by hand, but if we have Desmos, might as well throw it into the calculator. You should know how to do it by hand. In fact, I encourage you to do it and test yourself how quickly you can do it by hand. If you can do it in less than 3 minutes, you're in pretty good shape. If you can do it in less than 2 minutes, you're in very good shape. Like, very good shape. I'm really impressed if you can do it in under 2 minutes. If you can do it under 3 minutes, it's like, okay, that's good enough for the AP exam. All right, let's see. We're going to integrate this pi integral from 0 to 4, and that's because we're taking the whole space. I know we already did from 0 to 4 in a sense, but we were doing 3 to 4 of this portion up here with different boundaries on the top and bottom. Now we're taking this f of x curve as the top boundary. Wow, that got really bad really quickly. We're taking the f of x curve as the top boundary and the x-axis obviously as the bottom boundary. So this is a disk because we're rotating it around one of the boundaries. And without further ado, let's see what this comes out to be. 4x squared minus x cubed. I'm going to be blabbing a little more when we're able to use technology because it does so much work for me so quickly. It would have taken me, like I said, 2 minutes to do that. So we get 490.2. In fact, a good practice is to round to the third decimal place, so let's call it 208. That's probably the best idea. Okay, first question down. Not bad. We did some areas, we did some volumes. Now what I want you to do after you complete a problem like this is I want you to completely scrap it from your short-term memory, remove it from your mind, and now clear your mind. It's blank. There's a white, empty paper in your mind. Close your eyes and visualize that. And you're about to start a new problem where you're going to put new figures and new equations on there. So again, wipe your memory of the past. If you're still thinking about anything from the last problem, clear it out now. Then with the blank paper in your head, your eyes are still closed. You're going to get ready to write some stuff on there, okay? So slowly open your eyes and start writing down some numbers, some figures, some equations. Here we go. A tank contains 125 gallons of oil at time t. So I'm just going to call this G of 0 equals 125. During the time interval from 0 to 12, oil is pumped into the tank. So this one is in at a rate. So this is a derivative. This is the in derivative, and it's just some equation. I'm not going to look at it too carefully. 2 plus 10 over all this crap. I know that looks like absolute value. It's not. It's just brackets. During the same time interval, oil is being removed from the tank at a rate. So this is a derivative as well. This is how fast it's coming out. So stuff's coming in and stuff's coming out. The overall change in the gallons, let's call it G prime, is equal to the amount in minus the amount out. So if at any moment 6 gallons are coming in, while at the same time 10 gallons are coming out, the overall change in gallons is minus 4 gallons per hour, per minute, whatever. Okay, so just keep in mind that their difference is the derivative of the number of gallons, the overall change in the number of gallons, not the gallons themselves. Okay, let's look at part A. And what happens a lot in these questions, guys, is they're going to give you two different rates, and they usually independently ask you about one or both of them. So here we're just looking at how many gallons of oil are being pumped in. We're not worried at all about the fact that some is getting pumped out. It's just asking us how much is pumped in. Sorry for that weird spacing. This is the interval from 0 to 12. I know it looks separate here, but it's 0 less than t less than 12. So how do we find the number of gallons? We have a rate of gallons. So the number of gallons pumped into the tank is literally just the integral from 0 to 12 of h. Okay, so just plug that in very carefully. Integral from 0 to 12 of 2 plus fraction 1 over 1 plus ln of, what was it, x plus 1? Is that what all that was? Yeah, 1 plus ln x plus 1. I'm just going to call it x. Oh, it's 10 on top. There we go. My mind neglected the 0. It's 0, so I just counted it as nothing, I guess. And there we have it. Very straightforward. Let's round to the third decimal place. Be careful on that. 70.571. Now, sometimes they're kind of lenient. They'll give you a tolerance of 0.001. So if you put 0.570, they might still give you the point, but don't chance it. Just round that third decimal place. 70.571 gallons. Make sure you put gallons. Okay, so that's how much comes in over the 12-hour period. Think about that. Even though some's coming out, from the part that's going in, that's how much is going in. Question B. Is the level of oil rising or falling at t equals 6? Well, I just said that earlier that the change in the gallons is the amount coming in minus the amount coming out. So if the level of oil is rising, that would mean more coming in. So this would mean that the H of T, in other words, the H of 6, is bigger than the R of 6. Because if there's more coming in than coming out, then we're going to fill up the oil, I mean. If there's less coming in than there is coming out, then the oil level is going to fall because there's more coming out. Okay, so we just have to check those things. As far as give a reason, this is basically our reason. We've confirmed logically that if more is coming in than it's coming out, it's going to rise, and if more is coming out than it's coming in, it's going to fall. So we just have to compare those. We have to check them. So plug in 6, and this is very easy to do. So we're going to say, what is 2 plus fraction 10 over 1 plus ln of essentially just 7. That's what that is. Okay, and then let's take a look at the other function. I haven't given that a gander. So this is how many gallons are coming in at the moment when t equals 6. Now here's a sine function. So the amount of gallons leaving fluctuates because sine fluctuates. The most it can be coming out is 12 at a time. All right. It's kind of weird that the amount being removed, this can be negative. This whole thing can be negative. What does it mean for oil to be removed at the negative rate? It's kind of weird. Anyways, let's plug in 6. This is just going to be 12 times sine of 6 squared over 47. And that's 8.3187. So we find that R of 6, which equals, what was it, 8.318 technically. Oh, 319, sorry. Is greater than 5.395. That's what it would round to. Which is equal to H of 6. Oil is falling. Oil level at t equals 6. Okay, not bad at all. Let's try to pick it up a little bit. We're going to make some more progress here, but a little quicker. Part C, how many gallons of oil are in the tank at t equals 12? So what we need to do is we need to understand how much went in from H and how much came out from R. So we're going to use this here. And we're going to say that G of 12 minus G of 0 by the fundamental theorem of calculus is equal to the integral from 0 to 12 of G prime, which is the integral from 0 to 12 of H minus R. But that just gives us the overall change in the gallons over time, which is important. Trust me, it's very important. But we also need to consider how much is initially in the tank. That's why we have this G0 here that we're actually going to add on the other side. Because the amount of change is one thing, but the amount that we started with is going to help us determine the total amount of gallons in there at the end. Okay, so we can basically just plug this into the integral calculator. Let's do it. So we're going to take the integral from 0 to 12 of, we already kind of have the h of t here. Now we're just going to subtract 12 sine of x squared over 47. Let's see, is that correct? 2 plus 10, 1 plus ln x, that's h of t. This is how we double check. We look at the function 2 plus 10 over 1 plus ln of x plus 1. 2 plus 10 over 1 plus ln of x plus 1. Good. That minus 12 times sine of x squared over 47. 12 times sine of x squared over 47. Good. We're going from 0 to 12. Good. and that gives us negative 2.974. Negative 2.974 plus the original amount of 125 for a grand total of 122.026 basically gallons. That's how many gallons are in there, because overall the integral part we use the calculator for tells us that overall about 3 gallons has been removed from the tank, the net change. And that's in a complex process of stuff being added and stuff being subtracted simultaneously. But at the end of the 12-hour period, we have 122 gallons because 3 were removed, but we started with 125. Okay, part D. At what time is the volume of oil in the tank the least? So we want to find when the gallons are a minimum. At what time? And we're going to be able to use a calculator for this for sure. So we just want to say G of T is a minimum on the interval from 0 to 12. So the things we consider for an absolute minimum is we consider the endpoints, which we already know. G of 0 is 125. G of 12 is about 122, something like that, 6. Now, we have to also consider when is G prime, G prime is 0. And we also want to know when it goes from negative to positive. So what is G prime exactly? Remember that G prime, the overall change in the gallons of oil, is equal to the amount coming in, the rate of incoming oil, minus the rate of outgoing oil, you might call it. So we just want to find out when does this equal 0. Well, that's really easy to do. We can put that on a graph, and we're only looking from 0 to 12. So let's graph this. Let's say y equals 2 plus 10 over 1 plus ln of x plus 1 minus 12 sine of x squared, wow, over 49. That's going to stretch it out a little bit. See what that does? It's kind of beautiful. If I have this over 1, it's very tight. But the more I stretch it out, 15, 47, right, the more spaced out it is, because the values aren't going to reach increments of 2 pi as quickly when you're dividing it by 47. Okay, so let's take a look at some of these points here. Here's where it equals 0, but that's going from positive to negative. So this is going to be producing a maximum. So we consider t equals 4.79. We're also going to consider, I think it's just worth mentioning that we're considering it, we're also going to consider 11.318. We're going to say here, we're going to say G 11.318 is a minimum because G prime of T goes negative to positive at T equals 11.318. And we know that it's only going to get larger from there, which means that by the time we get to T equals 12, we're at a higher value than it was when T equals 11.318. So they just wanted the time. That's all they needed for that problem. We could say hours. Okay, and that answers this 4-part question. Let's move on to question 3. This is the final question that we have, where we're allowed to use calculators. In fact, let's see how we're doing on time. Yeah, not too bad. We're on about pace of 15 minutes per question. Question 3, a particle moves along the x-axis so that its velocity from 0 to 5 is given by this equation. And we're given this, the particle is at the point x of 8. X is 8 at time t equals 0. So we can say x of 0 equals 8. That's an initial condition. And keep in mind that the velocity is the derivative. So they gave us a derivative and an initial condition. We're probably going to have to find the position function in some way. Okay, part A. Find the acceleration of the particle at time t equals 4. Well, that's really easy, right? We can just take the derivative. So acceleration is just going to come out to be, that's a cakewalk, 2t minus 3 over t squared minus 3t plus 3. And so a of 4 is simply going to be 5 over 7. That's like super easy, right, guys? Does it give us units? It doesn't give us units, so we don't have to put like meters per second squared or whatever. But that's what it'll be. You can double check it. Double check it with Desmos, you know. Don't trust me. Part B. Find all the times, all of them, suggesting more than one, in the open interval from 0 to 5, at which the particle changes direction. So what does this mean? This just means v of t changes sign. Now that's super easy to do. We're going to go to Desmos for that. ln of t squared minus 3t plus 3, was it? Let's go back and double check that I'm inputting that correctly. Yeah, t squared minus 3t plus 3. And notice that it picked up on me writing t instead of x, and it was cool with it. Usually I like to write x. And now t becomes a slider. X takes priority. Okay, so from 0 to 5, we really only care about this portion here. And it looks like it changes twice. Once at x equals 1, kind of makes sense, because if you plug in 1, you get ln of 1, which is 0. And then once at 2, because when you plug in 2, well, you also get ln of 1, which is 0. Fair enough. So we would just say, like, according to graph, t equals 1, t equals 2, particle changes direction. It doesn't even ask if it's like going forward and then backwards or what. It just asks, when does it change direction? So when VT changes sign, if you look at the graph of VT, that's when it goes from positive to negative or negative to positive or whatever. Okay, making quick work of this last problem. Find the position, at time t equals 2. Okay, so we're going to have to use a little bit of the fundamental theorem of calculus here. Keep in mind that x of 2, which is the time that we want to know about, minus x of 0, which is where it started, is going to be equal to the overall change in position, which means the integral from 0 to 2 of the derivative of position, which is velocity. And that means that the position at 2 is equals to that integral. Might as well write that in here now. Plus the initial position, which is what they gave us. They gave us an initial condition. Now, fortunately, we don't have to find the antiderivative and find an original function for the position. We just need to find the position at a specific value, which takes advantage of knowing the velocity. We don't have to know the position function. We can just know the velocity, which tells us how the position changes, and say, well, if you started here at some place, and I know how much you changed, I will know where you end up at. That is the idea here. So let's plug that into a calculator. Finish this up. Integral from 0 to 2. Notice we're still using the same function like quite often. Okay, so that's how much the position changed. Not very much position change. We can say 0.369. And then we were given the initial position as x equals 8 when t equals 0. So this is going to be 8.369. That is the position at time t equals 2. We could have found it at any time using that process. An integral from initial condition to whatever value they're interested in. Okay, part D. Find the average speed. Interesting. So how do we find average speed? Well, speed is just the absolute value of the velocity, right? So the average speed, instead of saying velocity equals displacement over time, speed equals distance over time. So what that means is we're going to have to find the average speed by doing the integral from 0 to, what's the time interval? From 0 to 2 of the absolute value of the velocity, which could be different from the displacement. It is definitely different. This is a very small displacement, and that's because, as you can see on the function, let's graph the function again. As you can see on the function, it goes positive, but then it goes negative for a bit, and then it goes to 0. So by the time we get there, we've gone forward quite a lot, but then we've gone backwards some. And by taking the absolute value of the velocity, we are considering all of that as positive distance. In fact, let's see that. Now we have all of this being positive distance, so now our distance is going to be the total area underneath this curve here. Let's go ahead and find the integral of that from 0 to 2. All right, there we go. There's the true distance, 0.741 over the time of 2. Let's make sure there's no new rounding kind of situation that comes from. I don't think it is. It should just be 0.37. See, 0.371. All right, that is the average distance. Sorry, the average speed. Unit distance per unit time. They don't really give us units here, so that's not the emphasis. All right, but that does it for these questions. So that was really fun, to be honest. I'm probably going to do a couple more like these over this weekend and over these last couple of weeks that we have before the AP test arrives. So hope you learned something. Feel free to leave any recommendations or any hard problems that you might be interested in having me solve. Ones that you would, see on the AP exam. That's the point. If you want me to just do really hard problems, trust me, I can find really hard problems, but I'm trying to prepare you guys for what is likely your task on the AP exam. I'm trying to simulate what the task is going to be like, because I have a fear that many students, even if you know your calculus, aren't really ready for what the test is entailing. Okay, so the more practice tests you do, the better. And using the technology, you'll see that I used it modestly. There were certain situations where I had to use it. There were other situations where I really didn't have to use it. Even in this situation earlier where I didn't have to use it, I decided to use the calculator. It saved me, 3 minutes, 2 minutes. Okay, so that's enough blab out of me. I'll see you guys next time on the non-calculator portion that I will be recording, where we have to do all of the problems with no calculator. We'll save that one for next time. See you in the void.